Hello everyone, welcome to the next lecture of the course Design of Power Electronic Converters. In this session, we are going to study the single phase H-bridge inverter, also called as single phase full bridge inverter. The H-bridge inverter converts DC input voltage into a controlled AC output voltage. It is again widely used in motor drives, electric vehicle, uninterrupted power supplies. It's used in solar inverter system, battery energy storage applications. So in this lecture, we will first understand the H-bridge circuit, its switching modes. We will then study what is bipolar and unipolar pulse width modulation. And finally, we will solve a numerical problem involving the design of an H-bridge inverter supplying a DC motor. So let's begin with the learning outcome. So after completing this session, you should be able to explain the operation of a single phase H-bridge inverter. You should also be able to identify and interpret the output voltage and load current waveforms for both the cases, bipolar and unipolar PWM. We will compare the two pulse width modulation techniques based on the voltage transitions, current ripple, harmonic performance, electromagnetic interference. At the end of the lecture, you should be able to select a suitable PWM technique for the inverter that you are planning to design and perform the basic converter rating calculations. So let's first understand the construction of an H-bridge inverter. So this is the structure of an H-bridge inverter. Or this we have already done the studies in power electronics subject in the second year. So these are the four switches, and this is the load connected. So load connected point, and this is the output voltage terminal. The circuit contains these four power electronic converter. Then these are denoted by TA plus, TB plus, TA minus, and TB minus. So TA plus and TA minus, these two switches forms the first leg, leg A. TB plus and TB minus represents the plug B. Okay, this line is an extra line showing on it. Actually, the current is flowing through the load. Okay, current can be flow in both the directions. So let's see how the direction will change in the various modes of operation. So here the load is connected between the point A and point B. So this is your load. The output voltage V output is equal to VA minus VB. So this output voltage across the load is equal to VA minus VB. Each switch is provided with an anti-parallel diode. You can see the anti-parallel diodes over here. These diodes provides path for the load current when an inductive load is connected and corresponding controlled switch is turned off. Like if the load is an inductive load, there is a chance for the discharge of stored energy. So that discharge can be flow through the anti-parallel diode connected across the MOSFETs or IGBTs, whatever switching device we are using. The most important safety rule in this circuit is two switches of the same leg never be on at the same time. So that mode of operation is called a shoot-through condition. So it is not allowed to have a shoot-through condition if both the switches in a leg is turned on simultaneously. the positive and negative terminals of the DC supply, these two terminals will get short circuited, and this condition is called a shoot through, and it will damage the inverter circuit. So in practical inverter circuit, a small dead time is therefore introduced between the turn off of one switch and turn on the another switch, so that shoot through is not supposed to happen in the circuit. Now observe the switching state table. TA plus and TA minus are turned on. That is diagonal switches, TA plus and TA minus. The point A is connected to the positive of the DC supply through the switch TA plus, and point B is connected to the negative of the supply through the point TB minus. So here the circuit will be starting from the source TA plus, load, then TB minus, back to the source. So this circuit will be acting in the first case. Okay, so at that time you have seen that the load is directly connected to the source. So the output voltage is plus VDC. So you will get a plus VDC as the output voltage. Now next cycle, these two switches TA plus and TB minus will turn off, and TB plus and TA minus will turn on. So the circuit will change, like the negative will be connected to this switch, then to the load, then to TA minus, back to the source. So the current direction is this. So this side will be plus and this side will be minus. So opposite side of the load is connected to the positive side of the supply, and this side is connected to the negative side of the supply. So you can see that the voltage, output voltage is minus VDC. And if TA plus and TB plus, see, the switches from the upper leg is turned on, then the output voltage is 0. TA minus and TB minus turned on, that will again give you a 0 output voltage. So you should not turn on one leg together, it will make shoot through. If two simultaneous switches in lower leg or upper leg is turned on at a time, it will create a zero state. So for an H-bridge inverter to work, always opposite switches should be turned on. So thus the H-bridge inverter produce three possible output voltage: plus VDC, minus VDC and zero state. So this is our plus VDC. Then next can be a zero state, then minus VDC. So this will continue. So in that way, you will get a AC output voltage. So this is the working of an H-bridge inverter. Now, this slide explains the four valid operating points which I have already explained in the previous lecture. Current, we have four modes of operation. So in mode 1, you can see that TA plus and TB minus is turned on. Current flows from the positive terminal of the DC source through the load, from the point A to point B through the load, and then through TB minus to the negative terminal. The output voltage is plus VDC, and the load current flows from A to B. Load current flows from A to B. Now, next case is here again there is a correction in the direction. Current is flowing from A to B, not from B to A. This is the direction. Arrow should be drawn like this. A to B. Okay. Now in second case, TA, TB plus and TB minus is turned on. Okay. So when TB minus and TA minus is turned on, current flows from B to A. This direction is current flows from B to A. So output voltage is minus VDC. And in mode 3, upper two switches are on. Okay. So when upper two switches are on, there is no chance of any current flowing through this. There will be freewheeling through the upper switches. And if lower switches are on, again, there is again freewheeling through the lower switches. There is no voltage across this. So the output voltage waveform is plus VDC minus VDC, plus VDC minus VDC. This is the pattern of the output voltage. So the H bridge can therefore apply a positive, negative or zero voltage across the load while allowing the load current to continue in either direction. So current is also in positive, negative, positive, negative direction. Voltage can also be positive, negative direction. So four quadrant capabilities are also possible over here. This makes this suitable for reversible DC drives and AC motor drives. So when you are, especially when you are having regenerative braking possibility, you need bidirectional inverter. So this can be used as a bidirectional inverter. So these are the key points. H bridge can apply positive, negative or zero voltage across the load. This allows a reversal of current direction through the load. So this is used in widely DC to AC inverters, motor drives, UPS and renewable energy sources. Now we will move on to the pulse width modulation. So there are two types of pulse width modulation. One is bipolar pulse width modulation and the other one is unipolar pulse width modulation. So first of all, you should understand one thing, that pulse width modulation is a technique to make switching pattern for these switches. Okay, we know that we have to turn on these two switches for getting the positive half cycle and turn off TB plus and TA minus for getting the negative half cycle. Okay, so we need to turn on and turn off these switches continuously to get an output voltage. Okay, so pulse width modulation is a method to generate pulses, and these pulses are given to the gate terminals of each and every switches. Accordingly, switches will turn on and turn off. So how we can generate the pulses for turning on and turning off the switch? For this, these are IGBTs or MOSFETs, that is voltage control device or fully controlled device. So fully controlled device peculiarity is like when you are giving a positive output or positive switching, it will turn on the switch, and if it is zero, switching is zero, it will turn off the switch. So here in bipolar pulse width modulation, a sinusoidal reference signal, you can see the sinusoidal reference signal is compared with a high frequency triangular wave. You can see the triangular wave which is of high frequency. Whenever the sinusoidal reference is greater than triangular reference voltage or triangular carrier voltage. So here from this point to this point, you observe these 2 points. In these 2 points, from this point to this point, like this it will continue. At these points, the sinusoidal voltage is greater than your triangular voltage. Okay, in this condition, the diagonal pair TA plus and TB minus is turned on. So TA plus and TB minus is turned on. The output voltage is therefore plus VDC. You can see that the output voltage is plus VDC. whenever the reference is smaller than the carrier. So if reference wave is smaller than the carrier, okay, the magnitude of reference wave, the other diagonal pairs, that is TB plus and TA minus, will turn on. The output voltage become minus VDC. So this is minus VDC, this is plus VDC. So whenever there is a amplitude of carrier wave is greater, B plus and A minus will turn on, and whenever the reference wave is greater, A plus and B minus is turned on. So therefore a bipolar PWM output voltage switches from plus VDC to minus VDC. That's why it is called a bipolar. It is having two polarities, plus VDC, minus VDC. Notice that there is no zero voltage level in the bipolar output waveform. For this reason, bipolar PWM is also called a two-level modulation technique. So this is plus VDC, this is minus VDC. There is no zero level. So this is called a two-level modulation. Although the instantaneous output voltage is a rectangular waveform, see, you can see that the output voltage is a rectangular waveform. The average value over each switching period follows the sinusoidal reference. So you can see that the width of the pulse is increasing, then the width is reducing, then width is again increasing. So when you calculate the average of this square output pulse voltage, it is near to a sinusoidal voltage. So because of that, we can say that the harmonics can be eliminated. So when the load is resistive inductive, the load inductance opposes the sudden change in the current. As a result, load current waveform is much smoother than and approximately sinusoidal, although a small high frequency ripple is present. So here you can see that there is a small high frequency ripple, but still the output current waveform is sinusoidal in shape. The major advantage of this bipolar PWM is it is simple logic. Only one sinusoidal reference and one carrier comparison is required. However, every switching transition changes output voltage from plus VDC to minus VDC, from minus VDC to plus VDC. Therefore, the voltage step during each transition is equal to 2 VDC. That voltage step is 2 VDC. This large voltage transition generally produces high current ripple, and this may result in dV by dt stress, rate of change of voltage, sudden change in higher value of rate of change of voltage, which will create higher stress, and this will again create a greater electromagnetic interference. Now we will move on to another type of PWM, that is unipolar PWM. H-bridge circuit remains the same, but switching method is changing here. Okay, so here you will be having two reference signals. Okay, these reference signals are 180 electrical degree out of phase. Okay, usually it is having sinusoidal reference wave, which is 180 degree out of phase. Okay, the reference signal leg A is compared with a triangular wave to generate the switching sequence of TA plus and TA minus. Okay, so you can see that the output voltage is plus VDC minus VDC. The lower switch in each leg operates complementary with the corresponding upper switch while maintaining the required dead time. Okay, so here output voltage is unipolar, means individual pole voltage VAN and VBN switches 0 to positive, 0 to positive. So you can see that VAN 0 positive, VBN 0 and positive. So because of this, this is called a unipolar modulation, pulse width modulation. It is also called a 3-level output modulation. Here the output is positive. When the output is positive, inverter output generally switches between plus and 0, plus 0, plus 0, and next is minus 0, minus 0. When the output voltage required is negative, it switches between 0 and minus VDC. So comparing to bipolar PWM, it does not normally jump directly from plus to minus. It will go to plus, then 0, then minus, then again 0, and then plus. So voltage step transition is VDC, not 2 VDC. Another advantage is that dominant switching component in the line voltage appears approximately at twice the carrier frequency. So even both methods use the same switching frequency, but output behaves as though it is being switched at a higher effective frequency. So this results in a smoother current. So you can see that the output current is smoother comparing to the previous case. So now we will see the difference between bipolar and unipolar. So here in the case of bipolar, you can see that the output voltage switches from positive, negative continuously. And for the case of unipolar, it is positive, 0, like that it is continuing. Then after one cycle, it is negative, 0, negative, 0. So switching is happening in that way. So this is the difference between unipolar and bipolar. Then, however, this PWM, bipolar PWM is simpler comparing to unipolar PWM method. So most of the time, bipolar PWM is selected for simple and low cost application. Okay, and if you want better quality, then you will go for the unipolar PWM technique. Now we'll move on to the numerical problem related to this. We need to design an H-bridge inverter. A DC motor is supplied through a single phase H-bridge inverter using unipolar PWM. Motor operates in continuous conduction mode. So these are the given data. VDC, EA, I0, every values are given. Then we need to calculate the modulation index, duty ratio for all the switches, for individual switches, switching time, turn on time, motor inductance, minimum motor inductance, and converter ratings. These are the solutions, questions that you have to solve from the numerical. So we will solve the first part. First part of the question is like you have to calculate the modulation index. We know that modulation index is EA upon VDC. EA is given as 120 in the question, and DC link voltage is given as 200. So modulation index is 120 upon 200. It is 0.6. So average output voltage equals motor back EMF. It is in the minimum speed condition. Now you have to find the duty ratios. Duty ratios of the upper switch is 1 plus m divided by 2. That is 1 plus 0.6. 0.6 we have calculated, divided by 2, that is 0.8. It is for TA plus, and TA minus is 1 minus TA plus. 1 minus TA plus will give you the duty ratio of TA minus, so that will be 0.2. Similar way you can calculate the duty ratio of TB plus. TB plus is 1 minus m divided by 2, that is 0.2, and TB minus is 1 minus DTB plus, that is 0.8. So these are the values of duty ratios for all the 4 switches. Now you have to calculate the switching time period. Time period is the inverse of the frequency. Frequency is 20 kilohertz. So inverse of 20 kilohertz is 50 microsecond. Now turn on time of each switch. So for each switch, we know the duty ratio, we know the switching time period. So duty ratio into switching time period will give you the turn on time for each and every switch. So here you can see that uh, A A plus T. A plus is turned for 40 microseconds, A minus turned on for 10 microseconds, TB plus also turned on for 10 microseconds, and TB minus turned on for 40 microseconds. That is A plus and B minus should turn on in same time period. A minus and TB plus should turn on in the same time period. They are complementary to each other. Now you have to calculate the motor inductance voltage. So here for a motor VL, motor inductance is equal to VDC minus EA. This is a DC motor. So VDC minus EA. Here VDC is 200 and EA is 120. So this is 80 volt. Okay. So for 0 voltage state, VDC is equal to 0. So you will get minus 120 volt. So this is the inductance voltage, 80 volt and minus 120 volt, minimum and maximum value. Then minimum motor inductance. What is the value of minimum motor inductance? D is equal to EA upon VDC, that is 0.06 duty ratio. And a ripple formula, L is equal to VL max into D into TS divided by delta IL, which will give you 80 into 0.6 into 50 into 10 raised to minus 6. Substitute all the values. Delta L is considered as 1. So you will get the inductance value is 2.4 millihenry. Now you can calculate the peak current. Peak current is I naught, average current plus delta IL by 2. That will give you the peak current. So 5 plus 1 by 2, that is 5.5 ampere. And minimum switch blocking voltage is 200 volt. Your switching voltage should be 200 volt because your supply is 200 volt. VDC is 200 volt. Minimum peak switch current rating is 5.5 ampere. That is the peak value of your current, 5.5 ampere. Switch block voltage is 200 and peak voltage is 5.5 ampere. Okay, so when you are practically designing this, you have to add a safety margin along this. Like you should not take the exact same value. You should take a higher value than the uh, result you have obtained. So let's summarize today's session. So we have completed an H-bridge inverter, which is used for a controlled switch with the two legs. This will convert a DC input to a reversible AC or controlled AC. The inverter can generate three possible output levels: plus VDC, minus VDC, and 0. For the case of bipolar, it switches from plus VDC to minus VDC. Control of bipolar is simple, but voltage step is from plus VDC to minus VDC. Okay, then unipolar PWM is PWM. Two inverter legs are modulated separately. You will be having two separate reference signal. The output has three levels: plus VDC, 0, and minus VDC. We have also solved a design problem. We calculate the modulation index, switching duty voltage, switching duty ratios, switching time, motor inductance voltage, minimum inductance, and converter rating. So before concluding, let me remind something. Remember, most important practical rule. Never turn on the upper and lower switches of the same inverter like simultaneously. So whenever you are designing practical inverter switch, you should keep this into your mind. So I hope the basic design of an H-bridge inverter is clear for you. Thank you for your attention. So with this, we have concluded the first unit of design of power electronic converter. Simultaneously write all the notes of whichever videos that I have shared already and try to solve the numericals by yourself. So we have completed the design of buck converter, boost converter also. Now I will share you the design of buck boost converter also, then design of H-bridge converter. So these many things are there in your first unit. I hope this is clear for you. Please message me if you're having any doubts on this.